Good morning. One thing that I found out, so yesterday I turned on the Stellar website for this term. There's not a tremendous amount of information. There's the syllabus and the 2 lectures I've given last week, but I know Professor Eager's got some of his stuff electronically, so as far as the pile of paperwork you receive, we'll be able to give post some of that as well, so you can just save it for future use if you want. I believe the website from last fall and last spring are still there. So if you want to do those modules, it's probably helpful for you to go there. At least I know my part has the PDF of the lecture notes. So to follow the videos, it would be something probably useful to you. I'll probably post a link on the new page, but if you look into the calendar for last year, somehow I think the Stellar website is archiving the previous work, and if you can't see it, I can always add you. You just need to email me. I can add you to the class list. Another piece of information that I find very helpful is we have access through the MIT libraries to the whole series of handbooks from the American Society for Materials. The metals handbook, and there's also some engineering handbooks. So we're going to go there quickly just so you see the amount of information that's out there. So we're looking at metals handbooks. There's an alloy center, but all these from volume 1 to 23, it takes a whole shelf, or if not 2, to store all that, but you have access to it electronically. And for your project, if there's a topic that's interesting you, a chart for example, well, I'll typically do a print screen and organize it so I can essentially use the information for my report. It's a tremendous amount of information. You can do some search. Like this morning, I wanted to have some information about the Sharpie V-notch test, so I just typed it in, and you get here they talk about how you do the test. So it's quick to get at. It's a lot more reliable information than if you do a Google search, and it's also something that you can refer to if you're putting together a term paper or if you're doing some work. It's not something that you can do. Say you graduate, you go work for a small company. It's not something that is necessarily cheap, but obviously the ASM handbooks in mechanics and material area are very helpful to have some form of access to. So I would say take the opportunity to at least look at it, and I'm sure when you have some basic question, well, how does that really work? There's a whole chapter on it that essentially is available to you anytime. So that's my sales pitch for ASM. Used to be in the committees. It's a great organization. The goal of ASM is really to transfer information and make information available to the users. It doesn't really sponsor any standards or any kind of specific research work. It's really more of a network, and it will end up accumulating information in the form of those handbooks, and it has a few journal publications and stuff that can be useful as well for finding out what's going on, and you have access to those as well. So today what I wanted to do is to go back just a little bit on joining, because I know I've been throwing at you a few things about fusion welding, and we also talked a little bit about welding plastics, but I want to come back to it just so we close the loop and we move on. So moving on for us is going to be to talk about steel. I've already said steel was used a lot for fabrication because it's cheap and because we have a lot of methods to put it into a final product in large volume at reasonable cost. So we'll talk about the BOPs here when we talk about properties of steel. So this is the image I had from this project where I said they were using very thick PVC piping for secondary containment of high risk biological waste. And you're looking at a butt joint. So a butt joint is essentially taking two sections of pipe. So say I have one round here going this way. So I'm putting another one right next to it. And the idea is to put those two together. Now, if you look on a section here, what you'll find is just two pieces like this. And we're going to do top and bottom. So on the image I shown, you can see the welded bead. There are actually 3 beads there. And the way they made the joint is from the outside, they had a bevel. Both sides, yeah. So a 30-degree bevel here, 30-degree bevel there. And then you have the same bottom. And this is essentially adding to, it's doing 2 things. It's adding between for the contact between the welded bead and your base metal. If you have it, say I just weld it this way, which is done sometimes. So I got the 2 butt joints, and I come in here and I put a bead. Then I hope that this bead is penetrating and it's getting some of the thickness in the process. But I don't necessarily have a guarantee of that. What I know is I'm touching here and I'm touching there. So by creating that notch, you increase the amount of interface, you're increasing the contact between that bead and the base metal. The other thing you're trying to achieve, if you made that pipe, a certain thickness, this is a schedule 80, so it could be, what are we looking at? Probably 3/8 of an inch, 1/4 to 3/8 of an inch. It's very thick. There was a reason. You wanted it to be strong, but if you're loading it in tension in this direction here because of bending in service, you'll have a notch. If you weld this the way it's done there, and maybe I shouldn't even try to reproduce it, but it's something like this. There you go. You have a notch, and your strength in the axial direction is definitely less than half the strength of the full pipe, because you only have half of the throat. So sometimes we speak of throat as being the effective height here that's welded. As long as this is not as big as the thickness, I'm going to have a reduced strength. I know that. I just don't know exactly how much. And it will vary if it's an overload fatigue, and then it will vary depending on the material. But the idea here is they should have done a deeper notch. Now, there's a consequence to it, because say I come and now I make a notch all the way through the thickness. How much more welding do I need? At least 3 times, right? Because you got to fill this, which is what you had before. Then you have to fill this and this at 3 to 4 times more welding passes before you're finished. So when you have the option, what you do for those joints is you actually do it from both sides. Oh. So it will look like this. And that is only, double the amount of welding as opposed to what we have on the schematic there. So just from, this is all essentially geometrical, what we've been talking about. But the point I was making in our last lecture about plastics is this is really melting the PVC in more or less ambient air. So what they do is they come with a heat gun and they provide both heat. So say we're trying to do this well right here, or this one. So we're doing the root pass here. We provide the heat, and we also provide a shielding gas. So we're blowing a gas that doesn't contain oxygen to prevent oxidation. So nitrogen could be an option, argon. Depending on what you're trying to do, you'll use a certain chemistry of gas that will come on the surface and try to protect the metal that you are, the plastic in this case, but metal would be the same concept. I mean, we're really talking the same thing. The problem with this, if you want to bear with me, is when you do the root pass, because you can protect the top surface, say this is melted and it's filling the space, but you can't protect this back face easily, at least not with the same tool. There are ways that are used in pressure vessels where they're essentially going to pump, or they're going to circulate a shielding gas inside the pipe as well to prevent the oxidation of the degradation of the root. But in most cases, you'll have an issue there. And you know, in this image, we even see there's a porosity that is a hole. But it wouldn't be uncommon. You don't expect the root of the well to be the strongest part for, you know, this is one of the reasons. The other reason, it's really a stress riser. And it's a location where you have shrinkage forces. There's so much going on in welding that you can't expect that all of it is going to be perfect, especially the root. So that's where we talked about in a previous lecture about trying to get the joints out of the high stress zone. So instead of doing this butt joint like we have here for plastics, we use fittings a lot. And I wanted to go through one type of fitting that is used a lot. This is used for a lot of both residential and commercial. You have it for drainage, for waste drainage, and you also have it for fire sprinklers lines. You have it for a number of rigid plastics, essentially. Most of the time with rigid plastics, you have these fittings that you apply what we call a solvent cement on them. It's essentially a liquid, and you can see it here, the red thing after it dried out. It contains polymers and it also contains solvent. And acetone is a big component, but there are more complex solvents into it. What happens is when you apply the solvent cement and you slide the, say in this case you slide the pipe inside here, so this is the end of the pipe, so they're applying it on both sides. You put it together, and a lot of time, within less than a minute, you really can't pull it apart because the solvent is transferring relatively quickly to the surrounding plastic, and it's therefore distributing, and that makes the joint essentially not solidified, but dries out more quickly. The beauty of this system that comes across in a variety of forms, and you can get these glues, like if you put together a central vacuum system, that's typically what's in there. It's a very thin PVC plastic pipe that you put this solvent cement and you put it together. It's in the form of a lap joint. And what happens is the solvent is doing the equivalent of melting both sides, both the fitting and the pipe. So when you insert them together, you are mixing the molecules. You're mixing the molecules from the pipe with the molecules from the fitting, and that's what is giving you the strength after it dries out. Now, and I think you're probably going to get this idea from the whole class, including all the examples of Professor Eager, that nothing is perfect. Every once in a while something happens. So in this case, what you're looking at in the image is you may see, the little cracks that are forming adjacent to this solvent cement drip. So this drip is not something that you want, but it comes if you're putting too much of it and if you're not wiping it off. And what happens in those conditions is now all the solvents are degrading your plastic, and if you have the shrinkage, some shrinkage force here creates the tension to initiate cracks. Now, in this case, there's also the service stress. It's a hoop stress, and you're looking, this was the direction of the pipe. This was actually inside a pipe, so it's hard to wipe it off. The only thing you can do is avoid having it in the first place. But it speaks to kind of a counter effect where when you have too much of this, for the same reason that it's able to essentially melt the surface, it can degrade it as well, especially if you put the load. One aspect with this is if you put the load, if you put the pressure in the system before it's fully cured and before all the solvents are evacuated. There's a flush procedure you can use to try to move away the solvents quickly, but you're not supposed to pressurize at the same time, and who knows on a construction site if they're really going to just flush and not test it, see if they have leaks at the same time. So it's a technology that has been proven to the extent that it's used an awful amount, and it's not really a concern with regular drainage systems or the vacuum systems in general, because you don't have a lot of stresses. But for sprinkler pipes, the pressure inside these little pipes is really high, and it's not absolutely uncommon to have issues. So maybe now, after we talked about this, you can interpret this schematic a little better. And because I've introduced it too quickly, we're just going to go through it better this time. So we have a round bar that's essentially on a flat, and then it's going at an angle. So what this component was doing is, when you have a joist, you have what we call the upper chord, lower chord, and you got a bunch of diagonals going through it. So that's an example. We're looking at this diagonal, which is a solid piece, and instead of being this way, it's actually like this. That allows for room to put the weld here on the side of it. And when you look at it on the cross sections, that's what you're looking at. You're essentially looking at, so if I put the tubing right here under, and that's continuing as well, and it's a hollow core. So now, hopefully we can agree this is thicker, because this is a solid piece, so it's thicker than this component here. And if I want to weld them together, I'll need to put more heat in this component. And that's what they did. If you look at this, the image here on the cross section, there's quite a bit of melting here. There's melting on this side as well, and there's no melting here. So it's almost, if we're looking at the low fusion case, It's essentially as if they put the torch going this way, with most of the heat going on the round bar, making a welded bead this way. And one thing that I didn't mention is what we call the dissolution ratio. So there's that amount of metal from the bar that you're going to fuse along with the filler metal gives you an idea on how much, what's your efficiency. Or you can have autogeneous welding, like TIG welding, if you don't bring a filler metal. If you just come with inert electrode to provide heat here, the only thing that's going to happen is you're going to melt and make a pool out of those two metals without adding any metal. And it works in some conditions. It's used, the example of the butt joint, the one we have on top, you can do that because in reality you don't really need, if you put the two pieces butt one against each other, you can just fuse them as opposed to adding metal to it. In this case, we do want to add metal. One of the reasons is we don't really have too much metal in the first place on this tubing. So by adding the metal, you're only going to melt a certain amount out of each component, hopefully. And that's where the skills come in as far as controlling the arc, so it doesn't always stay on the same part. The arc on a geometry like this will tend to be trying to go in one direction against the mass, and you have to weave a little bit to get it on the other side. It's just not the easiest weld to make. You know, I'm taking this as the extreme example. If I just had a T-joint that I come and I put a fillet weld on each side, well, most of the time I don't have to worry about it. I can almost come with at 45 degrees in the corner if these are similar thicknesses, and I'll get a good joint. It doesn't mean I'm going to penetrate all the way in there, and therefore if I have a pull force here in this direction, I can still be weaker than just having a real T. If I was to forge a real T, this is the area I would have to transfer the load from this component to this one. Well, this is likely to be stronger in fatigue than having twice the interface. And I'm going to draw it so say if I'm fusing like this, having this and this, for this loading, because I have a crack. I have a crack in this one. Now, in bending, going this way, that's another story, because in this condition, the welds are actually reducing the stress concentration as opposed to having a sharp corner here. And it's not uncommon that you do have some bending loads on a T connection like this, and therefore you want to minimize the risk of defects at all these toes. So we call this the root of the weld, and this is the toe. You want to minimize the risk of defects at that toe, and the good news about that is it's easy to inspect. You can look at it visually and see if you have good fusion or not. So when I say good fusion, what I mean is I'm going to do another T. Good fusion has essentially a bead that has some convexity in most cases. Sometimes it can be concave, so I'm going to put it also as this. But you don't want to have it as a corner bead like the plastic ones. If we go back, these beads are really not, they don't like to be on that surface. They just want to, they have a lot of curvature to them. You can see it's like glycerin. You can see here that it's just forming that bead on top of our melted surface. So to be able to say that we have a good bond and we have good fusion, what would happen instead of being 2 half rounds, so I have the surface here and I have 2 half rounds right now. So I want these to have a lower angle where they start, and they're probably going to look like this. This is when you have enough heat into your base and enough adhesion, or you reduce the surface tension between the 2 pieces that you're joining when you provide sufficient heat. So this is an example of enough heat. This is not enough heat, or at least it's very marginal heat. And one of the reasons for not, while the contractor here was not putting too much heat, is it was going to oxidize a lot more as you raise the temperature. But you essentially need to provide ways to accommodate that. So you're looking at these here, and that's exactly like I drew, where it's a very smooth transition, and you're looking at it here. It's a 90-degree turn. So the low fusion well is not that different from this example here. Any question on joining? Okay. Are you more satisfied, Steve? So the way I wanted to approach talking about the specific metals and plastics also is I do want to give a little overview about how they're made, what's their structure, and then we're going to talk about properties. So we're going to do that today for steel. This is the iron carbon phase diagram, or a part of it. And can you see all right? It's not something that comes across as much anymore, I think, in classes of material science, but it used to be considered one of the most important things. If you didn't know your carbon iron phase diagram, you didn't really know what steel was. The idea here is to show phase stability. That's what a phase diagram is for. It's built out of thermodynamics. So what is the stability of a certain phase at a certain temperature is what we're looking at. And there's a lot of information, and I'm going to walk through it with you. If we start and take the column for iron, so we say there's no carbon. Well, the diagram talks about, see, this is the liquid phase for 1538 degrees centigrade right here. So at that temperature, you start to solidify. I say start because you can see here that there are some liquid that will essentially, well, no, if it's pure, okay, so you solidify. Let's start with that one. You're in the delta phase. The delta phase, I can't show you a micrograph of it because it transforms back to another phase later. It's only a very high temperature phase of steel. After the delta phase, you have the austenite and gamma. So from about 1400 centigrade all the way to, where's the line here? You start somewhere around, this is not working, somewhere around 900 centigrade, you are an austenite. And what that means in practice is you have a face-centered cubic structure. And I should show it right now. So this is this one. That's what you get in that austenite zone. And as you continue cooling with steel, you become a body-centered cubic phase. That's the yellow one here. And there's a lot of steel metallurgy that is based on this transformation. Sometimes you want to avoid it, Sometimes you want to get it. And it depends on the application. What happens is this transformation from the face-centered cubic to the body-centered cubic takes a fair amount of reorganization of the atoms. And if you cool fast enough, you can avoid it. You can end up at ambient temperature with this structure, and that's what we call quenching for steel. And what happens after you quench, you can find different ways to have your crystal structure retransform into something you like. And that's what makes steel metallurgy interesting, because when you go through welding, what you do in welding is you heat up fast and you cool back fast. So you encounter the risk of altering the treatment that you imposed in the material in the first place. So you can essentially manufacture a bar of steel, and when it comes to putting it as an assembly, by welding it, you can change the heat treatment that you've put it on in the first place. So why carbon? Well, carbon makes this other phase here that's called cementite. And what happens with that phase is, well, it's very brittle. It doesn't deform. And it will form as soon as you start putting a little bit of carbon in the steel. If you cool down the steel slowly, there's a limit to it. There's a solubility limit, and that shows up in this paragraph. So as long as you put beyond 0.02%, you'll form some cementite when you're cooling at low temperature. So what I'm doing to you here is I'm blowing the left side of that phase diagram to look at this one. This is the most relevant for steel. So I should say, when we're looking at this, you see that liquid phase that goes to a point right here, a low point? That's what we call an eutectic. And it's pretty much the composition of cast iron. Because when you're doing a casting with steel, trying to solidify at those high temperature here, 1500, is very difficult. And you're going through a bunch of phase transformation. It's easier to add the carbon to the steel and lower the melting point, so you can cast from a lower temperature. You have less residual stressors. You don't have to eat as much. It's not as problematic for the molds. But the good reason why historically people would rather cast iron here with 4 or 5% carbon as opposed to steel. Nowadays we also have more and more technologies to cast steel, but it involves doing it at higher temperature. So in the cast iron, you can see you get more of that cementite, and without getting into all the details, it's a good reason why it's making it more brittle. I mean, there are other reasons, but I think for today's lecture, all I want to say here is the whole phase diagram points to you to a condition where you'd like to cast, and that's for cast iron. And when you go to the left-hand side is where we have steel, and that's where we're going to focus for now. Structural steel will tend to be at about 0.2% carbon. I mean, there are different variations, but I'm just going to use that as a starting point. So 0.2 is right here. A lot of structural steel has this composition. You can have higher carbon if you don't have to weld it. And by higher, I know like a 1045 steel, you can make a heat treatment on it and you'll be around this level. So in that case, you can quench and temper it and get some good properties out of it. But then it's not really a material that you would want to weld. So the more you go towards pure iron, the more weldable you tend to be, because you don't go through as much of that transformation. That you can't really avoid the formation of that cementite. And forming cementite is not a bad thing. Think of it this way: is you can take that carbon and leave it everywhere in the microstructure. That will make it very strong everywhere, but also very brittle. Or you can segregate it. If you cool slow enough, the carbon is going to get together, form a cementite that's more or less like little pieces of log in the river. They don't necessarily contribute to how viscous the water is. They're just there in some locations. And that's a little bit what happens with cementite. Now, as soon as you start cooling faster, and I believe I got a graph of this. When I say cementite, that's this zone here that's got black and white. The faster you cool, the smaller would be the spacing between the different cementite layers, the different black layers. And that's what gives you strength. Now, strength comes most of the time at the expense of ductility, but this material in general, because you got all these grains, the white grains here are pretty much pure iron, and they're very ductile. So this whole structure is ductile. It doesn't have the maximum strength, but it's something that you can deal with most of the time, and you can weld this structure. What becomes more difficult is when you get this lat type martensite here. So we're going to go to martensite now. Martensite essentially is what happens when you cool very slowly, very fast. I'm sorry. You cool very fast, and what happens is you go out of equilibrium. The martensite, you can look at it in this phase diagram. You know, we have the cementite, we have the alpha phase, the ferrite here, we have the austenite. There's no cementite. The reason is it's not an equilibrium phase. It's something that happens because you don't allow for something else to happen. So what happens when you quench, and that's something that I want to get into the details right now, is you go from, instead of going from this phase to this one, you go to another phase that's called a cementite. It's not a cubic. It's very close to a cubic. It's a tetragonal phase. So think of it as this one, except that it's stretched a little bit. And the reason it stretches to make room for the carbon. And this whole transformation essentially happens without having to get all the carbon together in the form of cementite. You make your network able to fill in and accommodate the carbon. It's not something, again, that's really stable. So when you get it from quenching, if you heat it back up, now you can get some transformation, some different transformation to happen. And that's really something that's very particular to steel. It's not particular to steel that quenching it will make a different structure. What's particular to steel is how it's strengthening it. And not only strengthening it, there's a volume increase that's associated with that transformation. Because it's hard to accommodate that carbon when you get to a low temperature. Everything tries to get together in a compact shape, a low temperature equilibrium, and then you have that carbon that you need to accommodate for. And you don't have the time, again, to diffuse it into cementite. That's why you form that martensite. So we're looking here. This is a different type of diagram, and you don't have to remember all of this, but it's good for you to know it's out there. It's a cooling curve. You have different types of cooling curve. This one has two lines. One is for the center of the part, and one is for the surface of it. So obviously the surface is going to cool faster than the core. The heat comes out of the exterior surface, so it will cool faster on the outside. So what you see is you start at 800, and the horizontal axis is time. So over time on the surface, you manage to cool low enough that you reach the Martensite transformation before you get into other phases, but not in the core. So the core, is the other curve, gets essentially a softer interior than a surface because it's going to hit that Bennett. A Bennett face, I don't have a picture, but it essentially has some form of cementite into it, but it's very small. And that's why it's stronger than the perlite. So perlite here forms at high temperature. It'd be the softest. And then you go to benite, that's essentially a tighter microstructure, and you're increasing the strength. And when you go to Martensite, now you're very hard. You have a very high yield strength, but you're also very brittle. And I talked about quenching, and what I would say is most of the time, if it's not for a wear application, after you quench, you're going to reheat your piece and have it go through a benite transformation or some other transformation to get some ductility. But it's so if you manage to quench the whole part before you reach the benite tip here, and then you reheat it at a constant temperature, you get the opportunity to get properties that are about the same everywhere. And it's an advantage that a lot of people will take advantage of. It allows you to get both strain and ductility when you're in kind of a benite regime. Well, anything unclear about that Martensite, quenching, tempering? So the name for reheating is tempering. It's used a lot in automotive components. It's not used much for building steel, but a lot of components have heat treatments in aerospace, automotive, transportation in general. The big wheels for trains, for example, have to go through some special treatment. Now, there are other ways to strengthen steel. So we talked about the carbon here. This is showing how much you need to add of an element to change the yield strength. So when you see the positive slope, that's carbon and nitrogen. You have phosphorus. It's very rare we use phosphorus for strengthening, but it does have a strengthening effect. Silicon, copper, manganese we use a lot for strengthening. Molybdenum is more expensive, so we use it mostly for corrosion resistance. When you could get into stainless steel, we can use it also for strain. And chromium is reducing the strain. So it gives you some idea of other things you can do, and some of these elements will actually get into, our austenite and our ferrite and all of that stuff. They will stay in this crystal structure as opposed to forming precipitates like carbon does. And that's why you have less of a strengthening effect for a certain composition. I do want to point out that most of the time we're using steel as a wrought product. So you start it with a liquid, you will form a big billet or a strip. So these are the two ways here. You have two rollers to solidify very quickly your liquid. This is a more traditional way to forming slab billets. What happens is you form dendrites. Not all the time, but in most cases you form some dendrites in this process. And dendrites here, I don't know if they're simulated, but it's essentially something that grows, and it's an instability. So it means that it will push some of the alloying elements away. It needs to find its way, and it pushes all the impurities away. What happens with the impurities, they solidify last. So you get into a segregation situation in solidification that you want to get rid of by doing all that working. So if you start from a billet this big and you roll it, you deform it, you're gradually mixing in not only the little porosity and all that, but also you making the composition more homogeneous across your workpiece. And that's really to avoid this. So this is the surface of a billet. So you have the skin here, then you transition and you have your core. It's all, so this is directional. Eventually it becomes more equiax in the middle. You don't want that as a part generally, especially if you're going to machine this. We were talking about aerospace and starting from a big block going to a small block and machining it. The idea was to get homogeneous properties. So the only way you're going to do it is starting something this big, making it this big, this thick, and then machining it, because you get to break all that casting structure. Say you've casted something or you worked it, like and we're looking at fastener here and we're looking at treads. You see that layer? That's extra carbon. It's easy to add carbon or nitrogen to the surface of steel to make the surface stronger. And it's really used mostly for wear application. In this case, was to have the fastener self-drilling. So they have a surface that's essentially a drill bit, but the core still has toughness to serve as a structural component. It's a very delicate balance between being able to drill into another piece of steel and at the same time have enough toughness for service. And what's on the inside is still Martensite. So you're not looking at a piece that is very ductile. These are the three, so this is not in words. Now we have some numbers for strength of Martensite, benite, and ferrite. So if you go to a benite that's still a stable structure, you see, that compromise I was talking to you about, you see you can almost get to the point of Martensite, but you're also going to have some ductility as opposed to when you're essentially 100% Martensite. So we're looking at very, very high strength here. 1200, so that's more than 150 KSI. Steels in general, I think we're ready for that, is very adjustable for strain. So what we talked about, the ferrite and the pearlite leads you to pretty much most of the structural steel for buildings. And automotive is mostly in this area, except some critical component. You have a 4340. What that means, the last two numbers means 0.4% carbon. So we are pretty much in the middle of that diagram, where the maximum was the optimum for cementite was at 0.8. You can get to very high strain with these alloys and still have fracture toughness. Now we'll talk more about fracture toughness in the next class, but I do want to get all the way to what we call here trip steels, because it does tie into everything we talked about, that Martensite transformation, creating volume. It's a way to get both yield strength and toughness of a material. If you find a way to process your steel, obviously here it says you have 18% nickel, there's cobalt, there are different alloying elements. We're not talking about just steel. We're spending some money on alloying it, but you can have some retained austenite. That's the FCC phase, the one that is at the high temperature phase. If you keep some of this one here, the brown one, all the way to service, when you start to try to crack the steel, you'll have tension in the area of the crack tip, and that can induce the transformation to martensite, and it essentially grows the amount of material that you have to resist, and it's lowering the stresses. So it's a very interesting strengthening mechanism that we can make use of in real application. And I'm essentially going to close here to say it's very helpful. It's obviously more expensive. You have to go through processes to get your strain up to that level and still retain austenite that will transform as needed. But it's how you end up getting a toughness that's still above 100 KSI square root of inch just with steel. This doesn't have to be a composite, and all of this is kind of the reason why I said we still use steel for landing gears, because we can't beat it for strength and toughness. So there's a lot to learn about marrying steel and trip steel. So trip steel means transformation induced plasticity. And so you get the deformation of the crack tip by going to a martensite that has the extra 4% volume. So we'll take it from there tomorrow at 11 o'clock. Thank you.